Okay, so let's get started. I'm going to, in this session, continue with the discussion of floating point arithmetic, and we'll also have some discussion of when exceptions arise uh, and how you might want to handle exceptions, like an underflow or an overflow. Okay, just a little bit of review from the last time. This is how we think that our numbers are being represented in binary. So we've got one bit, which I'm calling S in this expression. This is for the sign. It's either 0 or 1. And then we've got some a number of bits for the exponent, right? So again, there's 11 bits. I'm calling that E over here. So you can represent numbers. So you can represent 2 to the power of E, okay? And then we have a whole bunch of other bits. A 1 is understood, and then you got 1 point B1, B2 up to BP. Okay, so there was an insightful question last time that if I use this scheme, yes, there's a question?
Sir, I had an idea about the thing that we talked about last time, where how do we represent zero in
Yes.
this scenario? Sir, so I was thinking that if we use a bias, right, we could just adjust that bias, and according to that, we can establish zero value.
Okay. Well, the weird answer is that there are actually 2 zeros.
Minus zero and plus zero.
Minus 0 and plus 0.
Yeah,
And it's
and
represented by, you either have your first bit, the sign bit as 0, and everything else is zeros, or you put the sign bit as 1, so minus, and then everything else is zeros. And that's how the IEEE represents, the IEEE standard is for representing
isn't
zero.
that kind of wasted though? Because Professor, I
Kind
was
of
looking
weird.
at it and like,
Um,
yeah,
I assume that there's some reason for it, but I hadn't been expecting that there would in fact be 2 zeros, but no. So that's how it is. Okay, so E, the exponent is 11 bits, and then you've got 1 point, the 1 is understood, I guess, unless it's 0, and then it's B1, B2 up to BP, and in our case, P is 52 bits, but you could imagine that, I don't know, going forward, maybe there'll be 128 bits or something, right? But I think the general idea would remain the same, however many bits we have for the mantissa. Okay, and then there's a question of, you cannot actually represent all possible numbers in this way. And, 0.1, 0.2 will not be represented exactly. And so when we want to talk about this, we'll talk about this floor function of x. This is the closest floating point number to x. Okay. And again, what if you have 2 such floating point numbers? Well, we'll choose the one with a 0 in the last bit. Okay. Okay. Exceptions. If x exceeds the maximum possible floating point number, we set that to infinity. Well, what's infinity? Well, you have to come up with a representation for that. And the representation is 0 for the 0 for the sign bit, all 1s for the exponential bits, and all 0s for the for the mantissa. But what will be displayed on the screen for you might be something, depending on the language, it might be something like INF or something like that. Okay. What if it's less than the minimum possible floating point number? Okay, we talk about minus infinity, and its representation then is a 1 for the sign bit, all 1s in the exponential bits, and all zeros in the mantissa. I'm not trying to make you experts on the IEEE 64-bit representation. You should have an idea of how these things are done. There is a way of storing the idea that you have exceeded the maximum possible number or you've gone below in the other direction. Okay, so there's a way of coding that. Okay, if you divide a floating point number by plus or minus infinity, what should be the result? Well, probably the result should be you've done something silly. You know, maybe there should be a flag for you if you've done that. Okay. Okay, and we had the idea of the machine epsilon. With this representation, the best you can, the smallest non-zero positive number that you could come up with would be 2 to the minus 53. So which is roughly 1.1 times 10 to the minus 16. Okay, and so that's useful to know. You know, I suppose it's trivia, but it's also useful to know because we are going to be looking at things like round off errors and so on and so forth, right? So if the round off errors are like 10 to the minus 16, we're probably not going to be too worried about them. You know, if they're considerably more than 10 to the minus 16, then we might be more concerned about them, for example. Right? But there's no point in worrying about errors that are less than the machine epsilon. Okay? Okay. Now, yeah, there's a question?
So is the machine epsilon a limitation of the bit architecture we're using, for example, 64-bit,
Yeah,
or is
yeah.
it a hard limit?
We got this 2 to the minus 53 by looking at how we represented
Mantissa, okay.
using the 64 bits that we had allocated. This was the smallest positive number that we could come up with. So right. Yeah, it's a limitation of those 64 bits that you have. You can talk about things that are smaller by either doing a scaling, for example, or you can try and solve problems like that in software. But using software to handle very large numbers or very small numbers it's a lot. It will take a lot longer to do your computations using software than just sort of innately in the hardware. Okay. All right. So when silly things are happening, when you've done something bad, then there should be some way of warning you, right? I mean, somewhere along the line, something has happened. You've, I don't know, divided by 0 or something. Now, whatever the results you're getting, they're not numbers anymore, right? And there should be some way of signaling to you, to the user, that at this point, we're no longer talking about numbers. So I think Python usually uses this notation nan, N-A-N, not a number. Back in the day, I used to see things nan q, not a numerical quantity. Okay, but there has to be some sort of a signal to the user that something has gone wrong. Okay, so that representation, again, I don't expect you to memorize all of these, but I just want you to know that there is, in fact, ways of representing this within the 64 bits that we allocated. So you can do 0 for the sign bit, all 1s for the exponentials, and all 0s, and then 1 in the final bit in the mantissa. up to, so in that range of binary numbers that I'm showing you on the screen, those are ways of coding that what you're dealing with now is not a number. You divided by 0, you multiplied 0 by infinity. Yeah, there's a question?
Sir, don't these values represent some other numbers?
Yeah. Okay, so in the, I modified the notes, the lecture notes, because of that previous question about how you represent zeros and things like that. And I've given a link to a nice Wikipedia article that goes into details about all of these things. Okay, so for a fuller description, more than I want to discuss here, because my main concern is not the 64-bit architecture. So there's more discussion in that about these representations using the 64-bit standard. So I'm just mentioning here a few things that might be of interest to us. Okay, but you're right. Obviously, then there should be some way of handling these numbers, right? How do I interpret this? If I'm interpreting this as not a number, then how do I write the numbers that it looks intuitively like? It's an interesting question. Yeah, I'm not sure what the answer to that is. Okay. Was there another question? I saw a hand raised.
No, sir. I had a similar question, so I'm gonna look it over the link that you have added to the
Okay,
slide.
right.
Thank you.
Okay, signaling a NAND. Well, okay, so the NAND gets sent to the floating point processor. Now, so you can make a distinction. You get a loud NAND or a signaling NAND, and that means that it sends a signal to the floating point unit, and presumably it shuts down the floating point operations. Okay, and you might have a quiet NAND, and then no signal is sent to the floating point processing, and then presumably you get nonsense. I mean, personally I think it's better to know when bad things are happening than not, but there might be reasons why you want to why you don't want the processing to stop. Okay, so the idea is that when well, later on when we're writing Python programs and we're throwing up NANDs, they're telling us that something went wrong, and then we're going to do some hopefully intelligent debugging, which will help us to figure out exactly what went wrong. Okay, now I want to do a few examples using floating point operations and showing you where we might be, where some errors can arise from some of the basic operations. Okay, so let's suppose that I want to add 0.5 and 0.05. So that's a fairly straightforward sort of thing. Okay, now 0.5, using those 64 bits that we have, will be represented in this way that I'm showing you here. And the nice thing is now you can just go online and ask for how these things can be represented. You don't have to do it by hand. Okay, so I went online and they showed me that this is the way that you represent 0.5. And then I went online and yeah, it turned out this is how you represent 0.05. I hope I wrote that down right. But anyways, you get two representations using 64 bits for 0.5 and 0.05. Now, can you suggest how we might add those two together? Yeah?
Sir, so we just do, the add the mantissa and then add the other number
Uh,
in binary.
okay, remember the middle, okay, so the first bit is the sign. The next 11 bits are the exponent. And then the next bits are the mantissa, right?
Yeah.
Yeah. Now, we don't want to add them. So this says this is 2 to some power times something. And this is 2 to some other power times something. So before we add the mantissas, what should we do?
Excuse me, sir.
Yes.
We need to make space for the two decimal spaces by creating some exponential form.
Okay. Right. So if let's suppose I had something which is 2 to the 10 times something times some mantissa, and I have something which is 2 to the 12 times some mantissa. What I want to do is I want to get the exponents the same. Okay?
So are we going to pick just one of them, the higher one, 2 to the
Yeah.
minus 12?
So I'm going to take the smaller number, and I'm going to I'm going to make its, so I'm going to make its exponent the same as the one for the larger number. And then I have to do the compensating thing for the mantissa. Okay?
Okay, yes, sir.
Right. So if you look at the exponent for the first one and the exponent for the second one, to make the second exponent the same as the first exponent, I have to multiply by 2. Right? And if I raise the power of this exponent, then I have to be dividing the mantissa by 2 so that I don't change anything. Okay? So this is what I'm going to do. I'm going to modify the smaller number to get the same exponent, and then I'm going to align the mantissas and I'm going to add them. Okay? So I take the original number and I raise the power of 2. But if I raise the power of 2, if I multiply by 2 in the exponent part, I have to divide by 2 in the mantissa part, right? And dividing by 2 means just shifting everything over, adding a 0 at the beginning, and then shifting the mantissa over to the right, the original mantissa over to the right. Okay? Is that all right?
Yes, sir.
Okay.
Yes, sir.
So now I've got 2 numbers. This modified 0.05 now has the same exponent bits as the 0.5. Now I can just add the 2 mantissas together, and I add the 2 numbers, and now this is what I get. The mantissas are the same in both, so they stay the same. Sorry, the exponents are the same in both and they stay the same, and I've added the mantissas. Okay. Notice what happened when this shifted over, what happened to the 0? The rightmost.
We lost information there.
Yeah, we lost the rightmost 0, but because it's a 0, it doesn't really harm us, okay? All right. So now, and then we, like I said, we add the numbers. Okay, now let's say I'm going to add 2 numbers, x and y. Let's say the representation of x is like this. So this, these bits for the exponent, they look like 126, but remember we have a bias of 127. So this represents 2 to the minus 1. over here in the middle. Now let's look at the mantissa bits. I've written 1 in red because 1 is always understood. And then the first bit is 2 to the minus 1. 1 times 2 to the minus 1, or 1/2. So this represents positive 2 to the minus 1 times 1 plus 1/2. Okay? Now let's look at y. Okay? So here's a number y, which is represented in binary using those 64 bits, as I said. The sign is, okay, so the sign bit is 0, so that means a positive number. And then I've got the binary for 125. But there's a bias of 127, so this actually stands for, it doesn't stand for 2 to the 125, it stands for 2 to the minus 2. Okay? Now, if I look at the remaining 52 bits, I've written 1 in red because 1 is always understood, 1. Now the next one means 1 times 2 to the minus 1, plus 0 times 2 to the minus 2, plus 0 times 2 to the minus 3, all the way up to 0 times 2 to the minus 51. And then the last one is 1 times 2 to the minus p. P is 52. Is that okay? So I've got this x and this y. Now I want to add them together. So what do I have to do to y? Before I add them together, what do I have to do?
The same thing will make the exponent same.
That's right. So this exponent was minus 1. And this exponent, this here is 2 to the minus 2. Okay? So now what happens? If I raise this by a power of 2, so if I multiply by 2 over here, if I increase this number by a binary 2, right? Then I have to divide the mantissa by 2. And dividing by 2 in binary means you shift all the numbers to the right and put a 0 in the front. Okay? So I do that. I took the smaller number. I increased the power of the exponent. I increased the exponent by 1. Okay? So the mantissa has to be divided by 2. Dividing by 2 means shift everything to, add a 0 to the front and shift everything over by one space. And now the 1 that we had doesn't fit anymore, it falls off the end. So the least significant bit falls off the end when you divide by 2 in the mantissa. So the 1 is lost. Okay? Now we add the two numbers together. Okay? We add the two numbers together, which basically means the sign bit doesn't change, the exponent bits don't change, the bits in the mantissa get added together in a binary fashion. And we've lost the 1. Yeah, there's a question?
So earlier you said that losing 0 doesn't harm us, but now we have lost 1. So will that be something?
That's right. So, but what we're hoping here is because it's the least significant bit that we've lost, maybe it doesn't do anything too bad to us. Okay.
Professor, so I have one question. So in the previous class, we talked about the rounding and how it chooses the number with the 0 in the end, right? So it's rounding down. And here, because we're losing accuracy, we are also kind of rounding down. So are we in like our errors based on our computation, would they always be understated? Like would our answers always be understated?
I don't think so. I don't think that necessarily follows, but I'd have to think about it some more. Okay. All right. So, like I said, as an example, 0.1 cannot be represented exactly in these 64 bits, as we've discussed. 0.2 can't be represented exactly. And so when we add the two of them together, we get a problem in the last in the last digit. But like I said, this is probably not going to. Hopefully, this won't do something bad to us, right? Okay. Okay, so now we move on to subtraction. What do you think happens with subtraction?
So we repeat most of the first steps, like getting the power of the exponent same, and then we subtract it instead of adding it in the last step of the mantis.
Yeah, you're right. And you might have to adjust the sign, right? You might have to change the sign bit. Okay. All right, so align as for addition, right? Make sure that you've got the same exponents in both cases. Check the magnitudes of the mantisses. Change the sign bit if required, right? You have to decide which sign bit you're going to assign. So you check that by looking at the magnitudes. Perform the binary subtraction, and again, you normalize, right, with the assumed 1 at the front. Okay. Okay, so that's subtraction. What about multiplication? What do you have to do? Yeah?
We could, for, I don't know exactly, but for a whole number multiplication, we could just repeat the addition process a bunch of times and call it a day.
Yeah, I suppose. Okay.
Can we add exponents this time? Because like, usually we do that in general maths.
That's right. That's right. We don't have to, I guess we don't have to worry about alignment too much. We can just add the exponents to get the right power of 2. We would check the sign bits, whether the result should be positive or negative, right? If the signs are the same, the result should be a positive. So the sign bit would be assigned to 0. If the sign bits of the two factors are different, then we would assign them a 1 to mean a negative number for the sign bit. We can add the exponent bits, and then we can do binary multiplication on the mantisses. Okay, so we have x. Let's say we have x like this, and with the, again, an understood 1, and we have a y like this with an understood 1, and because the sign bits are different, the result should have a sign bit which is 1, right? And then you can add the mantisses. So you can add the exponent bits, and you can do binary multiplication of the mantisses. Okay, so if you multiply those mantisses together, you'll get 1, 1, 1 with an understood 1. If you add the exponents, you'll get 100. And finally, this is what the result will be. Okay. Okay. So division. Division is a little bit more complicated. Okay. So again, you would, for the signs, you compare the signs. If they're the same, assign a 0 to the sign bit. If they're different, assign a 1 to the sign bit. That's easy. For exponents, you can do binary subtraction of the exponent bits, and that's easy. Now, there are 2 choices. There are 2 choices for the mantissa part. Okay? So there's one choice which is called true division. So you have unsigned division on the mantisses. You do actual binary division and subtract the exponents. And in all of this, if we're saying we're using the IEEE 64-bit standard, then you have to remember about the bias, and you have to remember about the understood one in the mantissa. Okay. Turns out that true division is rather slow. Okay. There's another approach, and that is division by reciprocal multiplication. Okay. So that turns out to be faster. It's about as fast, a little bit slower, but it's about as fast as multiplication. Your results will not always be the same as with true division. Okay. So division's a little bit different. Okay. I'm only going to discuss hardware here. If we're talking about, like I said, if you're talking about there are packages or libraries for dealing with like really large numbers, for example, and then things are done using software, that's going to be somewhat slower. And there's a question of how many topics you're going to cover in a course. I've decided that software packages for such things are not going to be part of this course. Okay. Okay, so we talked about exceptions, and then the question is, how do you deal with the exceptions? Okay. Okay, so here's an example. Okay, so by double equals, we mean it's like a mathematical statement. So you're asking to check whether a mathematical statement is true or not. So here we're asking, is 10 to the minus 16 plus 1, is that identically equal to 1? And Python will tell you that it is. Okay. So what's happened there? What do you think? Based on what we discussed before, why is this happening? Yeah.
So because Python only accounts for a certain accuracy.
Yeah.
And so if there is like a different number at the very end of it, let's say 18 decimal places after that, it won't really account for that.
Yeah, that's right. Remember, 10 to the minus 16 was approximately our machine epsilon. Okay. So when we added these two things, probably what happened was something like this thing where we lost the bit at the end when we did an addition. So something like that happened. So when you perform that addition, you were just left with 1 as you had before. And then both sides evaluate out to 1. Yeah, there's a question, Ali?
Assalamu alaikum, sir. Why is there a point after the 1?
Let's see. Oh, just because I wanted to, probably because I didn't want to have it converting between, I wanted to be sure that it understood that this was a floating point number and not an integer, which it might treat differently. Yeah.
This is correct syntax in Python?
Yeah.
Oh, thank you.
All right. I mean, we'll discuss more Python later, but here I just want to point out that when this is one of those examples where when you add something and you lose a bit off the end in the addition, it could lead you into some difficulty, right? Now, if your code was depending upon this being false rather than true, you might have a problem, right? And you should be aware that this is where some problems might come from, and then maybe you can fix the problem if it comes up. Okay, So here, another example. So this sort of thing is called a loss of significance. I stole this example from Wikipedia, right? And I think this is a standard example that, I mean, I remember seeing it when I was in school. So I think everybody uses it. So this is the quadratic example. Okay. So let's say that I have a quadratic expression, and I'm going to assign, I want a quadratic expression. I'm going to assign some roots to it, okay? So R1 is this root, which is 1.786. And the other one, R2, is another root for a quadratic polynomial. And that's like 1.15 times 10 to the minus 8. So you have these roots with very different magnitudes. Okay. Now, what I do is, so you can use Sage by itself, or you can use it as part of Python. A lot of it is built using Python. But so let's just say that there's this language Sage in which you can represent polynomials in this way. Okay, so this represents a quadratic polynomial. In fact, if you multiply everything out, it has a power 2. Okay, for the x's. Okay, so there's your s, and we know the roots exactly. Okay. Now, let's say that I'm going to take, I want to know if I multiply it out as a polynomial, it looks like ax squared plus bx plus c. So a is the coefficient of x squared in S. B is the coefficient of x in this polynomial S. And I'll let C be the product of R1 and R2, right? The last term, the constant term in a quadratic polynomial, is the product of the two roots of the polynomial, right? Okay. Now, yeah, just to scare you, right? To make you aware that some very bad things can happen if you're not careful. Let's suppose that you say, oh yeah, I learned the quadratic formula way back in, right? So I didn't give you S this way. I gave you S as ax squared plus bx plus c, okay? And then I said, I want you to figure out what the roots are. And you say, oh, I even before I came to university, I knew this quadratic formula, right? So here's one of the roots. X is equal to negative b minus the square root of b squared minus 4ac divided by twice a. Okay, so that's one of the roots. And then so this is the smaller root, right? You get the other root by saying plus the square root. But okay, so what happens? If you go back here, the 8th decimal place, the 8th decimal place is wrong, okay? Now, there's a better way of doing this, and that is you take x1 this way, and you find the other root as x2 is equal to c over ax1. Okay? And if you apply the better formula, right, then you're going to get a better result for x2, for the second root. And what's working here is that numbers of the same sign are being added, and basically you're avoiding any problems that come from subtracting from the possible from the subtraction. Okay, so at least one thing that you should learn from this course is just don't apply, don't always apply the same formulas that you learned. Their numerical implementation may actually lead to issues. Okay. Another example. So let's say that I set up things using this approach. So I have a recurrence relation. And so I have a bunch of numbers, y1, y2, y3, and so on. And the way they're related is that yn is equal to 1 over n minus a times yn minus 1. And it turns out that your yns are equal to the integral from x equals 0 to 1 of x to the n over x plus a. Okay. All right. So let's try an experiment. We'll let the first number be y0 equals log of 1 plus a over a, and a is equal to 10. Okay. And eventually by y11, you will get repeated bad cancellations. Okay. And again, we want to rewrite things in order to avoid catastrophic cancellations. Okay. So once again, back to the question of subtractions. And you remember we had a theoretical discussion about the relative errors that can occur with subtractions. We have this issue that some cancellations are bad, and you want to try to avoid those. Okay, let's try. I'll give you an example with an underflow. Okay, so this is what the code looks like. P is equal to 1. For I in the range of 110, so I takes values from 1 to 110. I want you to, we'll see what P is. And P then, the next P, so we're getting a whole bunch of values for P. I'm going to multiply the preceding P by 5.0 times 10 to the minus 4. Okay. So what happens? The last few terms of the output, you eventually get to 4.94 something times 10 to the minus 324. And then when you multiply by, well, basically you divide by, well, multiply by 5 times 10 to the minus 4. Well, it underflows and you get zeros. And then after that, of course, once you've got a 0, it just keeps multiplying by 0, and you keep getting zeros. So again, there's issues here, and when you're dealing with something like this, maybe what you want to do is you want to try some sort of a scaling, or you want to check as you're going along. Once the numbers get below some value, I'm going to rescale the values and see, and then I'm going to scale back to get the actual numbers. But okay, so, you know, catastrophic cancellations, underflows, these are some things that you should be aware of. Yeah, there's a question?
Yes, sir.
Yeah.
So, sir, basically what I was trying to say is that this depends upon machine, right? How good a machine performs. So for instance, if we talk about the machines that were developed काफी like पहले बिल्कुल start में,
Yeah.
so their accuracy was like very low. They couldn't compute numbers इतने ज़्यादा.
Yeah.
So, and considering now the technology that we have, so इसमें like we can go to this small number, right?
Well, yeah, sure. But of course, if we move from, say, 64 bits to 128 bits, we could get much smaller numbers. But eventually there will be some set of calculations or some version of these examples which will break the equivalent codes, right?
Okay.
So we should be aware of this. No matter, these kinds of errors can occur no matter how many bits of precision we might have.
Thank you.
Okay, let's consider another example. So you have a function, f of x is equal to 1 minus cos of x over x squared. And I'm going to allow the values of x to go between minus 4 times 10 to the minus 8 to plus 4 times 10 to the minus 8. And we have to take out 0 because obviously otherwise we'd have a division by 0 squared, which would be silly. Okay, now for very small values of x, what is this? What should this be? Approximately. Think back to Calculus 2 and Taylor series. What should this be? Yeah?
Should it be a very large number?
Should it be? Okay.
It should be 1.
Right, right. Yeah. Maybe. Okay. What's the limit as x goes to 0 of 1 minus cos of x over x? Do you know? Okay. Does anyone know the Taylor series for cosine of x? For x small?
Even powers of x divided by the factorial
Yeah.
power, and you sum from
Right.
0 to infinity.
Right. So cosine of x is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial and so on, right? So if I take 1 minus that, what do I get?
So 1/2, 1 over
Right.
2.
Right. So I'm going to get I should be getting numbers that are close to 1/2. Okay. So we know what the answer should be, right? Okay. Let's see what happens. Okay. So once again, this is the Taylor series for that expression. So for x very small, I would like to get numbers that are very close to 1/2. Okay. All right. And in the limit as x goes to 0, I would expect to get it. I would expect to get numbers very close to 1/2. What do we actually get? Okay. I hope you can see this. What do we actually get? Yeah, we get some really bad results. Yeah. So what happened? Okay. These are the huge relative errors. Remember we talked about subtraction. You can get huge relative errors. So, this is what's happened here. Very bad result. Okay. All right. Now, the other things that you want to consider is that supposing you've got an if something, then you want to do something, and if not, then you want to do something else, right? And so what would happen if your conditional depends upon something which isn't a number, right? Well, the result is false and you might end up doing something silly. Okay, so check the numerical quantities that you're going to put into a conditional. Okay, catch that exception first before you feed it into an if-then kind of construct. Make sure you're not feeding it something which isn't even a numerical quantity. Okay. There any questions about that? Okay. If not, I'm going to upload some even worse or just as horrible, examples. Okay. Continuing with our discussion. Okay. Once again, remember the notation that we were using, the approximate number x hat and the actual quantity we're calling x. So the difference between those two is the absolute error, and the relative error is given by dividing by the dividing by the actual value x. So the relationship between x hat and x is that the approximation x hat is equal to the perfect number x times 1 plus the relative error delta. Okay, so that's what we had before. And what we would really like is that your deltas should be less than the machine epsilon. Okay, then you don't really have to worry too much about them. Okay. Now, we've been when we're discussing these errors, we're talking about the errors on the numbers. We also would do some preliminary discussion about floating point operations. There's some error which results from the floating point operation. Okay, so there's this perfect floating point operation, and then there's the actual algorithm which tries to implement the floating point operation, which I put a hat on top of. Okay, and so the assumption will be that if I take two perfect numbers, x and y, no approximation, so let's call that x plus y, or it could be x times y or x divided by y, any floating point operation involving two floating point numbers. So x plus hat y should be equal to x plus y times 1 plus a delta, and that delta, that error is coming from the some error in the implementation of the floating point operation. Okay, so for example, this is what it looks, one analysis for scaling. I've got x hat equal, so for squaring, sorry, x hat equals x times 1 plus the relative error on x. Okay, and then if I square that, I get x squared times 1 plus twice delta x plus delta x squared, but we don't really worry about the squared errors in this course. So we've got x squared times 1 plus twice delta x. So as we discussed last time, the relative errors double when you square a number. Okay. So relative error doubles, as I said. Okay. Another way of looking at this, and this is called the backwards analysis, is to say you're doing an operation on x, right? But I'm writing a hat above the f because I want f of x squared, but that multiplication, that binary operation might be giving us some, that floating point operation, sorry, might be giving us some errors. So I'm actually f hat is for the algorithm, and f is for the perfectly purely mathematical operation. Okay, so what we do is we say that f hat of x is x squared, the result that we actually want, times 1 plus an error which is related to f. right? An error which is related to implementing the operation as with some algorithm. Okay, and what I actually want, this would be equal to x squared times 1 plus some delta f tilde squared. For some delta f tilde, you'd have to work out what it is. And so that looks like the perfect operation acting on x times 1 plus some error. Okay. So the error in squaring a number without an error is like the error-free squaring of a number with an error. Okay. So probably explore these ideas a bit more in by giving you some questions or problems to work on. Okay. Once again, let me remind you, we had this result previously. If I have some number x and then I represent it in the machine, I get an error. I have a number y, I put it into a machine, I get some other error. If I multiply the two of them together, this is the result. And so essentially, and then we drop the terms beyond the first order in the error. And so the result is like the relative errors basically add. And what that means is that the relative error in multiplication is no worse than the absolute value of the relative error. Okay, the magnitude of the relative error on x plus the magnitude of the relative error on y. We had that result before, so I'm not going to have a long discussion. Once again, we also had the result for division. Just let me remind you again that in this time the relative errors subtract, and so the relative error should in the multiplication should be no worse than the magnitude of the relative error on the first factor plus the magnitude of the relative error on the second factor. Exponentiation to the nth power, we multiplied by n using our multiplication result. Okay, again, we had this before. And when we do addition, we found that the absolute errors add together. So the things are not going to get worse than the absolute error on x plus the absolute error on y. Okay. Subtraction gives you the same result. Okay. For the absolute errors. But once again, the relative error looks like this. It's the absolute error divided by the actual result that you wanted. So if the subtraction should give a very small number, so x and y are very close to each other, then you could potentially get enormous relative errors, and this will lead to a loss of significance. So let me give you an example. Let's say we want to approximate the derivative of sine function at x is equal to 1. Okay? And I say, well, okay, I remember. The derivative is approximated as sine of 1 plus h minus sine of 1 for h very small. Okay? So now what happens? I'll let you do the experiment. Put in h is equal to 10 to the minus 4. The relative error is 3.89 times 10 to the minus 5. Now put in h is equal to 10 to the minus 13. the relative error is on the order of 10 to the minus 3. Okay. Decreasing h increases the relative error. Okay. So once again, you might need to find a smarter way of evaluating that derivative. Okay. Now, this brings us then to ideas of stability and conditioning. But stability, maybe it's not so easy a thing to define. We sort of know it when we see it. It refers to the perturbative behavior of an algorithm, right? If I change one small thing and it creates a huge difference in the result, I would say that that algorithm is unstable. Okay. By conditioning, then I mean when we do this mathematical analysis of the problem, the conditioning is referring to that, right? Remember, we had the condition number. That's one way to talk about conditioning. Another terminology is accuracy. So and if f is the mathematical thing, then f hat is the, when I wrote a hat over something, I always mean that that's the algorithm or that's the representation in the computer. Okay, so x is the desired result, x hat is the computed result, right? F should give me x, but actually I'm using f hat, the algorithm, and it's giving me a result x hat. Okay, and when will we say that f hat is an accurate algorithm? Well, so this is we will look at the result that we get minus the result that you would get using the perfect algorithm, using the perfect mathematical f, and acting on x hat and dividing by what you should get, the magnitude of what you should get, which is f of x. And if that's less than on the order of the machine epsilon, then I'll say that f hat is accurate. Okay, what if the problem is ill-conditioned? Remember the condition number. If it's ill-conditioned, then we probably don't hope for accuracy, right? The problem is sensitive to perturbation, and you're going to get some rounding, whatever. Okay. Yeah, I can skip that. Okay. Stability. What should we? Okay, working definition of stability is that you get the right answer, well, or almost the right answer, using to almost the right question. Okay. And what we mean by stability may mean something different depending upon the context. Okay. All right. So that's definition is okay for numerical linear algebra. It might not be okay for ordinary differential equations. Okay. There's also a terminology, backward stability. It means that if I put in the exact number into the algorithm, or if I put in the approximated number into the perfect mathematical expression for f, and if the results are the same or almost the same for x's, such that the relative error on x is on the order of the machine epsilon, right? So if x hat is is very close to x, then we will say that this algorithm is backward stable. Okay, and that's a stronger condition than we've had for stability. Okay, so once again, back to our example. My perfect expression is f of x is equal to 1 minus cosine of x over x squared for some small non-zero x. Okay. Now I take the Taylor series for that. I expect results close to 1/2 for small x. And I remind you that this horrible thing happens. So let's do a bit of analysis. We'll start with the calculation of the cosine. Let's say that when I'm implementing the cosine, I'm actually implementing cosine of x times 1 plus some delta. And I'm hoping that that delta is less than or equal to the machine epsilon. Okay? So if I take 1 minus that, I will get 1 minus the cosine minus delta times the cosine of x. Now, what's the Taylor series for 1 minus cosine of x? It's, so what's the Taylor series, sorry, what's 1 minus cosine of x implemented in our machine? If I take the Taylor series for cosine of x, I will get 1/2 x squared plus delta plus order of x to the 4th terms. Right, so there are other terms, x to the 4th, x to the 6th, and so on, but we won't worry about those. Okay. Now, if I divide everything by x squared, right, then what do I get? I get 1 minus the cosine of x implemented in our machine divided by x squared is approximately equal to 1/2 times 1 plus delta 2 over x squared. Okay? So what's the relative error? Remember, the 1 plus something, that something is the relative error. So the relative error is approximately delta times 2 over x squared. What's happening as x gets very small?
So the magnitude of an error just explodes.
Yeah. So if x is on the order of 10 to the minus 8, then delta is on the order of 10 to the minus 16, right? Delta is like on the order of the machine epsilon, but the order of the relative error is order of 1. And you're dealing with results that should be 1/2, right? So, yeah. So very bad things can happen. Okay. So I'm sorry, should have had a few more minutes to do this. Okay, so what I would like you to do is to consider f of x equals sine of x over x. Okay? And I would like you to try and just copy and paste to the extent possible the analysis that we did for the cosine for the previous problem, the previous f. And I want you to make a prediction about the performance of the code, and then maybe you want to actually write a code and see if your prediction is right. Okay. And then if you're a real keener, I want you to look at this f. So what have I done? I've taken sine of x and I've subtracted off the first 2 terms of the Taylor series for sine, right? For x small, and then divided by x to the 5th. So you should be able to work out what result it should give you for very small x. And your analysis should tell you, you do a similar analysis, your analysis should tell you what result, what the actual, how good the results are likely to be. Okay. All right. So that's the end of the session. Are there any questions? Okay, then. That's our first week. And I will. Okay, Ali has a question.
Yes, sir, how does a machine calculate expressions like sine and cosine? Does it sum up the Taylor series? And if so, then to
Yeah.
what extent does it go far? How far does it?
Yeah, it turns out that quite often Taylor series are not the way to go, right? The result might be perfectly correct in terms of the theory, right? But summing up a Taylor series, I mean, you can use a Taylor series to say to represent pi as a summation, as an infinite summation, but it's going to be very slow for calculating accurate values of pi. So the Taylor series might not work. There are other, for numerical work, there are other more sophisticated series that might do better than a Taylor series. Okay. Are there any other questions?
Professor,
Yeah.
would an algorithm with a small backward error have a big forward error and vice versa?
I don't think so.
All right.
I mean, not
Thank you.
necessarily.
Okay. Yeah.
All right. Okay. I'll catch you next week.